Good morning, class. In our last session, we explored the concept of the derivative visually, understanding it as the gradient of a function's tangent line. We even practiced sketching the graph of a derivative, f prime of x, just by looking at the graph of the original function, f of x. Today, we're going to move from sketching to calculating. Our goal is to find an exact algebraic expression for the derivative. By the end of today's lesson, you will be able to find the derivative of power functions using the power rule, differentiate entire polynomials, and use the derivative to determine exactly where a function is increasing or decreasing. Let's start with a quick warm-up to refresh our memory on the relationship between a function and its derivative. On the board, we have two graphs. One is a function, which we'll call f of x, and the other is its derivative, f prime of x. Your task is to figure out which is which. Let's look at these two graphs. One is a downward opening parabola, and the other is a straight decreasing line. Take a moment to think. Which one is the original function, and which is its derivative? Okay, let's analyze this together. Remember, the derivative's value at any point x represents the gradient or slope of the original function at that same x value. Let's look at the parabola. Notice the very top of the curve, its vertex. The tangent line here is perfectly flat, meaning its gradient is 0. If the parabola is our original function f of x, then its derivative f prime of x must be equal to 0 at this x value. Looking at our line graph, we can see that it crosses the x-axis right at this point. This means the y value of the line is 0 here, which matches the gradient of the parabola. Now consider the left side of the parabola. As we move from left to right, the curve is going up, so its gradient is positive. If we look at the line graph in this same region, its y values are positive as they are above the x-axis. This is another match. Finally, on the right side of the parabola, the curve is going down, so its gradient is negative. And indeed, the line graph in this region has negative y values. So we can confidently say the parabola is the function and the line is its derivative. This graphical method is great for building intuition, but it's not always precise. What if we need the exact gradient at a point? For that, we need a formula. This brings us to the main topic for today, finding an exact expression for the derivative. There's a fundamental rule that forms the basis of most of the differentiation we'll do. It's called the power rule. The power rule states that if you have a function f of x equals x raised to some power n, its derivative f prime of x is n times x to the power of n minus 1. In simple terms, you bring the old power down to the front as a multiplier, and then you subtract 1 from the old power to get the new power. Let's see this in action. Let's take the function f of x equals x cubed. Here, our power n is 3. According to the rule, we bring the 3 to the front and subtract 1 from the power. So f prime of x is 3 times x to the power of 3 minus 1, which simplifies to 3x squared. It's that straightforward. This rule is incredibly versatile. It works for negative powers too. Let's consider the function y equals x to the power of negative 4. In this case, n is negative 4. We bring the negative 4 to the front. The new power is negative 4 minus 1, which is negative 5. So the derivative dy of dx is negative 4 times x to the power of negative 5. Now, what if there's a constant multiplying our x term? The rule is very similar. If f of x equals a constant a times x to the n, the constant a just stays out in front, and we multiply it by the derivative of x to the n. So the derivative is a times n times x to the n minus 1. Let's try this with an example. Find the derivative of f of t equals 2 times t to the 5th power. Here, our constant a is 2, and our power n is 5. The constant 2 hangs around, and we multiply it by the derivative of t to the 5th. The derivative of t to the 5th is 5t to the 4th. So we have 2 times 5t to the 4th, which gives us 10t to the 4th. Often, we'll need to use our knowledge of index laws to rewrite a function into this x to the n form before we can differentiate. Consider the function y equals 6 over x squared. This doesn't immediately look like our x to the n form, but we know from our laws of indices that 1 over x squared is the same as x to the power of negative 2. So our first step is always to rewrite the function. Y equals 6 over x squared becomes y equals 6x to the negative 2. Now it's in the right form. We can apply the rule. The derivative y prime is 6 times negative 2x to the power of negative 2 minus 1. This simplifies to negative 12x to the power of negative 3. We can also write this as negative 12 over x cubed. Great. We now have the power rule and the constant multiple rule. But what about functions with multiple terms, like polynomials? For this, we use the sum and difference rule, which is very intuitive. It simply says that if your function is a sum or difference of several smaller functions, you can find the derivative by differentiating each term separately and then adding or subtracting the results. In other words, the derivative of a sum is the sum of the derivatives. This means we can now differentiate any polynomial term by term. Let's look at the example y equals 7x minus 2. To be very clear, let's rewrite each term in the x to the n form. Remember that x is the same as x to the power of 1, and a constant like 2 can be written as 2 times x to the power of 0, since x to the 0 is 1. So our function is y equals 7x to the 1 minus 2x to the 0. Now we differentiate term by term. The derivative of 7x to the 1 is 7 times 1 times x to the 0, which is just 7. The derivative of 2x to the 0 is 2 times 0 times x to the negative 1. Since we're multiplying by 0, the whole term becomes 0. So our derivative is 7 minus 0, which is just 7. This leads to a very useful shortcut that you'll use all the time. First, the derivative of a term like ax will always just be the constant a. And second, the derivative of any constant term is always 0. This makes sense because a constant function is a horizontal line and its gradient is always 0. Now, a very important point. At this stage, we do not have a rule for differentiating a product of two functions or a quotient. We'll learn those later. So for now, if you see a function that's a product or a quotient, your strategy must be to algebraically manipulate it first. You need to expand any brackets or split any fractions to turn the expression into a simple sum of terms that look like x to the n. Let's see an example with a product. Let's find the derivative or rate of change of y equals the quantity x plus 3 times the quantity x minus a, where a is just some constant. We can't differentiate this directly. First, we must expand the brackets. Using FOIL, we get x squared minus ax plus 3x minus 3a. Now we have a sum of terms, and we can differentiate term by term. The derivative of x squared is 2x. The derivative of ax is just a. The derivative of 3x is 3. And 3a is just a constant, so its derivative is 0. Putting it all together, dy dx is 2x plus 3 minus a. Now let's try a quotient. Let's differentiate f of x equals the quantity x squared minus 6, all divided by 2x. Again, we must rewrite this first. We can split the fraction into two terms, x squared over 2x minus 6 over 2x. Now we simplify each term using index laws. X squared over x is x, so the first term is 1/2 x. For the second term, 6 over 2 is 3 and 1 over x is x to the negative 1. So the second term is 3x to the negative 1. Now we can differentiate. The derivative of 1/2 x is just 1/2. For the second term, we bring the -1 power down, so -3 times -1 is positive 3. The new power is -1 minus 1, which is -2. So the derivative is 1/2 plus 3x to the negative 2. All right, let's test this idea. It's a common place for students to make mistakes. I'm going to put a problem on the board with 3 different attempted solutions. I want you to take a minute and decide which one is correct, and more importantly, why the other 2 are wrong. The problem is to find the derivative of y equals the quantity 6x squared minus 5x, all over x cubed. Look at the 3 solutions. Which one followed our strategy correctly? Let's review. The correct strategy is to rewrite the expression as a sum of power functions before differentiating. Solution 1 seems to have differentiated the numerator and the denominator separately. This is not a valid rule for differentiation. We cannot just differentiate the top and bottom of a fraction, so solution 1 is incorrect. Solution 3 rewrote the function as a product and then tried to apply some kind of product rule, differentiating the 2 factors. As we've said, we don't have a product rule yet, and this is not how it works anyway. So solution 3 is also incorrect. Now let's look at solution 2. This student correctly started by splitting the fraction. 6x squared over x cubed is 6x to the negative 1, and 5x over x cubed is 5x to the negative 2. Now the function is y equals 6x to the negative 1 minus 5x to the negative 2. Differentiating this term by term gives negative 6x to the negative 2 plus 10x to the negative 3. This is the correct procedure and the correct answer. Now let's connect this back to the graphical ideas we started with. We can use the derivative to find out precisely where a function is increasing or decreasing. The rule is simple. The derivative, f prime of x, tells us the gradient. If the gradient is positive, the function is going up or increasing. If the gradient is negative, the function is going down or decreasing. So if f prime of x is greater than 0, f of x is increasing. If f prime of x is less than 0, f of x is decreasing. Let's use this to solve a problem. Find the interval of x values for which the function f of x equals 5x squared minus 12x plus 3 is decreasing. The question asks where the function is decreasing. This means we need to find where its derivative is negative. First step is always to find the derivative. Using our rules, the derivative of 5x squared is 10x, the derivative of minus 12x is minus 12, and the derivative of the constant 3 is 0. So f prime of x is 10x minus 12. Now we want the function to be decreasing, which means we need its derivative to be less than 0. So we set up the inequality. 10x minus 12 is less than 0. Finally, we just solved this simple linear inequality for x. Add 12 to both sides to get 10x is less than 12. Then divide by 10 to get x is less than 1.2. So the function is decreasing for all values of x less than 1.2. Let's do one more check on this concept. Is the function f of x equals 2x cubed minus 3x increasing or decreasing at the specific point x equals 1? To answer this, we need to know the sign of the derivative at x equals 1. We don't care about the value of the function itself, only its gradient. First, we find the derivative function. The derivative of 2x cubed is 6x squared. The derivative of minus 3x is minus 3. So f prime of x is 6x squared minus 3. Now we evaluate this derivative at our point of interest, x equals 1. We plug in 1 for x. F prime of 1 is 6 times 1 squared minus 3, which is 6 minus 3, which equals 3. The result is 3, which is a positive number. Since the derivative is positive at x equals 1, the function is increasing at x equals 1. Let's tackle one more complex example that brings a few of these ideas together. Let's find the derivative of h of x equals the quantity 1 plus 1 over x, all squared. Once again, we see a product and a quotient. We can't differentiate this as it is. What's our strategy? That's right, we need to expand and rewrite it as a sum of power functions. First, let's rewrite 1 over x as x to the negative 1. So we have 1 plus x to the negative 1 squared. Now we expand the brackets. This gives us 1 plus 2x to the negative 1 plus x to the negative 2. Now, it's in a form we can handle. We differentiate term by term. The derivative of the constant 1 is 0. The derivative of 2x to the negative 1 is negative 2x to the negative 2. And the derivative of x to the negative 2 is negative 2x to the negative 3. So our derivative is negative 2x to the negative 2 minus 2x to the negative 3. We could also write this answer using fractions as negative 2 over x squared minus 2 over x cubed. Excellent. Let's quickly recap what we've accomplished today. We introduced the power rule, the cornerstone for differentiating polynomials. We learned that we can differentiate functions with multiple terms by simply handling each term one by one. We established a crucial strategy. Always expand and rewrite products and quotients before you attempt to differentiate. And finally, we applied this new skill to analyze functions, using the sign of the derivative to determine where a function is increasing or decreasing. This is a foundational skill that we will build on for the rest of the course. Make sure to practice these rules. That's all for today.